species like Campylobacter. Okay, lots of them. It's a mesophile. Normal bacteria common. Some of the bacteria like heat. We call it a thermophile. This is somehow 35 to 80 degrees Celsius. Or maybe 55 to 80 degrees Celsius. Sorry. Yeah, 55 to 80 degrees Celsius. What's the example? Bacillus. And we will do a lab to testing the impact of temperature for bacterial growth. You will find the bacillus can survive at 55 degrees Celsius, and others are there. That's bacillus. Last section, thermophile. That could be 80 to 113, sometimes 120 degrees Celsius. Can survive very hot temperature. What is the example? One of the example is geobacillus. One of the bacillus, hyperthermophile. This geobacillus used to testing the effectiveness of autoclave. Because the autoclave temperature should reach 121 degrees Celsius. If the autoclave temperature reached 121, that is across the line of 113, geobacillus is dead. If geobacillus is still there, which means the autoclave is not good. Now, of course, the autoclave have to reach 15 psi at least. Okay, sometimes 20, 21 depends. 15 psi is definitely needed. Now, most of the hyperthermophiles is actually also environmental microorganism. Where you can find it, I mentioned earlier, is hot springs in Yellowstone. And you can find those hot springs, the fabulous color, lots of them hyperthermophiles. And it's very interesting. Lots of the people isolated the enzyme from the hyperthermophiles. There's a lots of the research topic can do because they can survive in a very high temperature. They could be used in the food industry, some of them. Okay, so just give you an example. Next one, we want to talk about water activity. Okay, this is a key concept. When we finish this, I'll let you go, but we want to finish talk about this one. 15 minutes, we want to talk about this. This is the key thing for water activity. Lots of the people will be confusing about this topic, about this concept. So water activity. Acronym AW. Okay, what is water activity? Water activity equals partial vapor pressure above a solution divided by partial vapor pressure above a pure water. Now, this we always put 1.000 there. This sounds very easy. Okay, we can say it is P divided by P0. But what is that? When you read all the textbook, even in my food science textbook, lots of people put that formula there. I don't think people get it. So that's why I have to explain to you. There's a little bit of physics behind that. Okay, what is looks like? I put a line there. We talk about the bottom. Is that called denominator? This is called the numerator. Okay, we talk about denominator first. What happened? It is a closed vessel right here. It's a closed vessel. Okay, the closed vessel, we're going to put water. Water molecule H2O, somehow H2O, lots of H2O, okay? You learn in physics. Some of them will be evaporated into the air. Evaporate. Some of them will be dragged down or stay in the solution. At the end of the day, they will reach a balance. When they reach a balance inside here, they will have some pressure. Comes out. This is called vapor pressure. And the vapor pressure of pure water. Now, little bit of physics. I say that this is a closed vessel. Outside, what's the pressure? Atmosphere pressure. Is that right? If the atmosphere pressure equals vapor pressure of the pure water, what's going to happen?
No evaporation.
They're going to have boring. They're going to happen. This is going to happen. So bubble going to come out. Then going to boring going to happen. And that boiling temperature, remember, relates to the elevation. In the Rocky Mountain area, you're cooking an egg, 94 degrees, 80 degrees Celsius, it's going to start to boring. In West Virginia, modern time, maybe about 94, never reach 100, because of elevation. So that's what's the partial vapor pressure. It is after balance. The evaporated water molecule in this closed vessel generated this pressure, we call it vapor pressure. Okay, now, let's say I have another vapor pressure right here. Instead of I add water, I'm going to add sodium chloride water. So there's a lot of ClO2, NaCl there. What's going to happen? They're going to drag out lots of the water molecule down here. So the water molecule evaporated here will be less than the pure water because the sodium chloride will drag them down. So this is much less water molecule in this vapor. So this is called partial vapor pressure for solvents. Because of you add a sodium chloride, or you, for example, if a sugar or protein, it's going to drag them down. So that's why the vapor pressure here is less than the pure water vapor pressure. This is what comes out. Therefore, the range of P and P0 is always equal 0 to 1.00. And I give you some example. For example, hot dog. The water activity is high. 0.995. That's why it is a big risk for foodborne pathogen. How about beef jerky? You like it dry? This is about 0.9. Once the water activity less than 0.85, the bacteria are not going to grow too much. And we also know if pH 4.6, water activity 0.5, this comes out with low acid foods. So that is what is water activity. Now, Cindy, you're going to have a question. I don't know whether you have a question, but when I was students, I have a question. What is the difference between moisture? You say the water activity is like that. When you see the water, there are lots of people will think about the moisture. And at one time, I asked my students, one of my graduate students, I said, what is water activity? He just tell me, the amount of the water in your food products. No, that's called moisture. Okay, so what is moisture? That is the amount of the water. So it's a difference. Now, is there a correlation between that? Yes. Now, lots of the textbook comes out with this equation, E or H. I don't think the people edited this book really understand. Then they come up with this E or H equals 100% multiplied by 1 activity. What is this? That is equilibrium relative humidity. That's related to what amount, and another expressway for what activity. So, moisture content is amount of water. Water activity is the partial vapor pressure divided by partial vapor pressure of pure water. What are the relationship? It is not that simple. We make sure it's your understanding, okay? This is water activity, or we say E or H. This is moisture. What is the relationship? A typical curve looks like that. And this curve, desorption, and that curve, absorption. And those two are never reversible. So think about it. If a food product, if you absorb water and the dissolved water is reversible, then food safety never be a problem. Because I could take out of all the water gone, then the bacteria are not going to survive. So when I need the water, I'm going to pump them back. Is that easy? But never going to happen because it's not reversible. So this is the relationship between water activity and moisture. So by other words, what is water activity really means? It means available of water can be used by bacteria or microorganisms. Now we want to talk a little bit more. It is fun. We draw this picture here. What is it really talk about? In food chemistry areas, they couple them, separate them into 3 different places. This is 0.2, this is 0.7, sometimes 0.25, sometimes 0.75. The first part, we call it some mono layer. This is additional layer. And the last one is capillary section. What's the first layer? They're going to talk about the products. You like it, chips. Very dry. And we don't care about the bacterial growth. Did you ever heard about outbreaks of listeria on chips? No, because it's very dry. But what we care, if you open the chips on the bench, and 3 weeks later you test it, it's going to become very sweet. That's called reversion, flavor reversion. It's a acidity of the lipids. So we are talking about is really care about is fatty acids oxidation. Okay? One of the second additional layer here the products looks like. Raisin or raisin. Now what's the reason we care about? We care about change the color. It's a Maillard reaction. We don't really care about the bacteria. Did you ever heard about outbreaks of raisin? No. But why here we could take care of it? This is what fresh produce and meat, beef, poultry meat in this capillary area. Because in this area, the water activity and the moisture, they are highly correlated. They almost, the curve is overlapped. At that moment, there's a huge amount of the water. The available of the water to be used by bacteria is huge. That's why we care about the safety. Therefore, you heard about fresh produce safety, cantaloupe by listeria, E. coli 157H7 by ground beef, Campylobacter salmonella by eggs, by poultry. You heard about those news all the time. The reason is that because there is a big amount amount of water available for bacteria use. That is the key. So this is the one, what I draw here is very well to explain to you what is water activity. This is the partial vapor pressure in a closed vessel divided by partial vapor pressure of the pure water. It tells you how many available water bacteria to use. There is a correlation between moisture amount, but it's not equal moisture amount. And there's a lot of story can talk about that. Okay? Last one, since we talk about the sodium chloride, based on the requirements of the sodium chloride, we could be categorized into major two. Sodium chloride, if you are less than 0.2 mole, we call it a halophile. Which bacteria is a halophile? We did Staphylococcus aureus. This is the reason Staphylococcus aureus is widely existent on the skin surface, because our skin has salt comes out. When you're sweating, like what I did, I played the tennis. I don't know whether you can see it. Some dry here, salt. I wear this in purpose because you can see the salt there. That some bacteria can grow. I bet lots of Staphylococcus aureus because they like salt. Okay? That's why Staphylococcus aureus can grow on skin surface. Now, if the bacteria can grow in the moisture more than 2 mole, we call it halophiles. We call it extreme halophiles. Where are we going to find it? Extreme halophile. Name a place. Great Salt Lake in Utah. Did you ever be there? Great Salt Lake? A lot of mosquitoes there, to be honest. In Utah. In Salt Lake City, you will find a lot of the extreme halophiles. They like salt. Without salt, they cannot survive. Okay, so this is something interesting, very interesting topic behind it. We talk about the water activity, we talk about the halophiles and extrophiles. Okay, so Thursday we will finish this section. Lots of we're going to talk the oxygen and also the bacterial media combination.